David, and a big call out and thanks to the organisers and particularly the elves for this being so fantastic a conference and last minute change to being remote. So what I'm going to be talking about today is joint work with Blanca Sarzo, who is just finished her PhD at the University of Valencia, and she visited me at the University of Edinburgh for a few months, and this is one of the projects that came out of her research visit. And it also involves Victor Elvira, who is now a reader at the University of Edinburgh. So it's really great to see some of these speakers coming before me covering some of the topics. I'm going to be picking up on something that Ricky talked about. And we're going to be looking at individual heterogeneity model, random effects models, but we're going to have a big data set. And one thing Ricky talked about was that these models are difficult to scale, sometimes depending on the methods you're using, and particularly for a Bayesian method, they don't always scale very well because of the computational expense that the algorithms will use. So that's what I'm going to be focusing on. I'll motivate the problem with some data, discuss why the problems arise for the Bayesian approach. I'm going to be looking to fit at relatively standard models to the data. And then the main thrust of the talk is developing a new approach which solves the computational expense. And I'm going to show some simulated results. Unfortunately, we haven't actually managed to fit it to the real data set yet, and that was partly because Blanca was finishing up her PhD, which was obviously more important at that point, and also I've been distracting her with something else. So the case study we're going to look at is a colony of guillemots on an island off the coast of Sweden, and it's the largest colony of guillemots in the Baltic Sea. There's currently probably over 15,000 guillemots present in the colony, but of course when we look at this then over many years, the number of unique individuals we'll have in our study can be much bigger, and we're going to be looking at a 10-year period between 2006 and 2016, and there we have nearly 30,000 individuals recorded, their individual recapture histories. Now if we want to fit a standard CJS model, we can calculate the M arrays, fit the model, absolutely no problem. So the scale doesn't matter when we have nice sufficient statistics to describe our data. But the CJS model is now a very standard basic model, and we often want to do more complicated things, and there's loads of extensions of CJS models. We've seen some of these throughout the conference, and we've seen several of these already within this session. And I've been involved in many of these over the years, and a lot of it is mainly the extension of these models is to allow for some other additional heterogeneity that we want to incorporate, and particularly at the individual level. And we can have observed covariates that help us explain this individual heterogeneity, or they can be unobserved. And the one I'm going to be looking at is the random effect individual heterogeneity model, so basically unobserved heterogeneity, that without which the models don't explain the data very well. And we're just going to the simple case where we have the survival probabilities have this individual heterogeneity component. I'm not going to discuss the models in details or anything, but just think we have this individual heterogeneity or random effect. And the problem is when we have this random effect, as Ricky talked about earlier, there's no closed form expression for the likelihood. We have to integrate out the individual random effect terms, these epsilons, and that makes the likelihood be analytically intractable. It's expressible as an integral. But that's not a problem because we know different ways of dealing with this. Ricky talked about the Laplace approximation. We can do the methods. I'm going to talk explicitly about the Bayesian data augmentation approach. And the way we do that approach is we actually treat these epsilons as parameters or auxiliary variables in the model, and then we can do a standard MCMC approach. We treat them as parameters, form the joint posterior distribution over the parameters, which I'm just going to denote by general theta for whatever model parameters are, and the random effects. Run a standard MCMC, explore that, and then we can marginalize the calculate, get a sample from the posterior distribution of the parameters given the data by just ignoring the epsilons. Straightforward, very easy to do. The problem we hit then was the quantity of our data. So we have 30,000 individuals, and even fit in simple models which are too simple to explain the data, this was taking more than a week in JAGs doing this data augmentation approach. And there's multiple reasons this was taking so long. First of all, we've got 30,000 additional parameters that we need to impute at each iteration of the Markov chain. And the dimension of theta is about 10 to 15, depending on what model you're specifying. So hugely more auxiliary variables than we have parameters, so we have to update each of these. But that's not the only problem. Probably more difficulty is that when we are introducing all these parameters, we introduce a lot more correlation. So actually we get really poor mixing in the Markov chain as a result of that. And then when we update our parameters theta, the calculation of the likelihood, the complete data likelihood, is much slower. So all this means we've got a slow chain, takes a long time to run, the number of iterations, and the chain mixes poorly. It's horrible. It just doesn't work and it collapses. So how are we going to address that? And what we're going to do is relatively actually simple idea. We've got this big posterior distribution that's slow to sample from. So we're not going to sample from that distribution. We're going to sample from a different distribution, a much cheaper distribution of the but is similar to the posterior distribution. And then we obtain our sample from this wrong, cheaper distribution, but because it's similar to the posterior distribution we're interested in, it's relatively straightforward and efficient to then correct those parameter values we've sampled via something called importance sampling. And basically, I'm not going to go into the details of this, but the idea is you give each sample set of sampled parameter values, you give them a weight, and the weight is predetermined based on your proposal distribution, this cheaper distribution, and your distribution of interest. And then if we want to calculate, for example, the sample mean of a parameter, rather than just taking the standard arithmetic mean of your posterior sample that you have, we take a weighted mean where the weights are given there to be the ratio of the true posterior to the proposal distribution. And you can do anything you want. You can also calculate posterior quantiles and so on. And often a simple way to do that is via sampling importance resampling. Rather than doing a weighted mean, you can just resample your sample parameter values where you sample them in relation proportional to their weights. And then you can do the standard things of calculating the means, plotting densities and so on. Now, for this to work well, it's critical that the proposal distribution is similar to the true distribution that we want, and that's the important part. So how are we going to do that? So what we're going to do is, we know that standard MCMC data augmentation works if we have a small data set, but it just doesn't scale. So what we're going to do is to split our data set into two parts. X1 is just going to be most of the data, and we're going to sort of siphon off a small subsample of the data, X2. And as it's small, and now a small data set, we can do standard MCMC on that. And that's what we're going to do. We use our proposal distribution being the posterior distribution of the parameters given our small subsample. And then we'll reweight those samples doing standard importance sampling. I'll briefly touch on how we're going to subsample at the end, and that it's important how we do that, but we haven't got time to go into the details of it. But theory is straightforward. There's a small problem that we have to address, in that if we look at our weight here, the weight that we calculate is the likelihood of the remaining data, the big data X1, but that's analytically intractable. We can't evaluate that likelihood. That was where we started from. However, we can get around that really nicely by basically replacing that weight. Rather than it being the exact value of the likelihood, we can estimate that. And as long as we use an unbiased estimate of the likelihood, all the properties, and we get the correct distribution, all that falls out. So we get everything works as long as we use an unbiased estimate of the likelihood. And for those of you who are familiar with MCMC and particle filters, the rationale for why this works is very similar to particle MCMC. It's basically exactly the same argument, but ported into importance sampling. So that's what we do. We can actually get an unbiased estimate of the likelihood, And we're going to do that via a stratified Monte Carlo approach, which again works fairly well and is relatively quick. Everything else stays the same though for the important sampling step. So we sample from this simpler or quicker posterior distribution using a subsample, and we just reweight those values. So let's see how this works in practice. So we do this for a simulated data set. I said we are going to, the next step is to do it on the real data set, but we just haven't got there yet. So we have about 10,000 individuals, and we subsample 20% of the individuals, and we can do this many times. So we could just do it once and it works, or we could do it low. And what we actually did this 100 times, and all these are independent of each other. So we can run, it's embarrassingly parallelizable. So we can just run all these. So the time it costs to do 100 is the same time it costs to do one, which in our case was 15 minutes. If we did the standard MCMC on the full data set, it took about 3 days to get reliable estimates. So this is what we have, the results. The red, the top of the density estimate, so this is just taken 4 subsampled posteriors. The red is the full one, and then these are just 4 other subsampled ones. And you can see, if we look at the estimate of sigma, they're quite, you can see they're roughly centered, but they have a bigger area, so they're more spread out. Unsurprising, because we're using a small amount of data, the precision is less, but they're, you know, sort of roughly in the right area. If we then do our importance sampling, what we get are these top plots. So you can see they're much bumpier because now our effective sample size is much smaller, because we get some particle depletion, but they are now much similar to the red one. And what we can do better again is to actually combine all these samples into another full density estimate, and this is what we do in the bottom plot, and now we can see we're getting really quite close for really cheap simulation. So, and again, just to show, these are the quantiles, it all works, and even with 4 we're getting basically really spot on estimates for 15 minutes work compared to 3 days. So that's the idea. It's relatively straightforward, we think. We have to apply it to the guillemots. We want to use a more complicated model, and there are things that we still want to improve on this. There are things we need to think about. I said I would mention this, come back to it, the subsample that we use, and we can do this stochastically or deterministically, it's critical. So you have to think carefully how you do it, but if you do it well, it really works well. And there's some really other ideas to try and improve this. So we're at early days, so any feedback is also welcome. And that's it. Thank you very much.